Hello, my name is Philip Velie. I am a second year at the University of Virginia studying physics and math, and for the last year and a half, I've been working with Professor Luidi studying photography. Today, I'll be giving a poster presentation on the imaging of the nucleon glue in C. Now, as a brief introduction and overview, generalized parton distributions, or GPDs, are very powerful tools that allow us to visualize the internal structure of nucleons. In particular, our functions were defined in terms of variables Bjork and X, zeta and T, and we initially parameterized our GPDs at an initial value of Q squared of 0.5 Jev squared, but after adjusting the model, we evolved them so that they would match current and future kinematical data at both Jefferson Lab and the EIC. Now, gluon and GPDs and quark GPDs pose a very unique challenge, as there is no universally accepted set of parameters. So to determine the best fit of parameters, we can create an algorithm that procedurally narrows in on a range of parameters based on a starting range. So the user we first define a potential initial range for each parameter and the number of points that we wish to test within this range. For instance, for mx, say the initial range was between 0.1 and 10, and we tested 11 points. They're equally spaced points inside this range. We do this for each one of the free parameters, and we get a set of combinations of these parameters. We then take these parameter combinations and create GPD curves, and from these curves, we calculate error values, in particular the root mean squared error, between these curves and existing models and data. We then select the combination that produces the lowest error and use it as a basis to construct the next range of parameters. Hence, this is a sort of cycle where it goes one cycle after the next, and the range of parameters then becomes the following. And this cycle continues for as long as you have computational time for, which is a not insignificant problem. An interesting result is that we can have different sets of parameterizations that obey the expected errors, but also have different values of parameters. For instance, in this curve here, we have the blue curve, which is governed by this set of parameters at a Q squared of 0.58, and this purple curve, which is another parameterization, but with a Q squared of 0.97. But you can see here, both of these curves will obey the expected errors, and they're also very similar to each other. However, the individual parameters themselves are different. We can then take a parameterization. From now on, I will be using this one in this table, and then we can evolve it to higher Q squared, as mentioned before, to match kinematical data. We can then see the impact of Q squared by studying its effect on the integral of the GPD. And you can see here in this blue curve, you can see these jumps, and these jumps are exactly what we expect, as these jumps occur as we are crossing the heavy quark mass thresholds in the strong coupling constant. And in addition, we can use this fitting methodology to study the effects of these different parameters on the different GPDs. I, in particular, studied HG, but I know this process can be applied fairly linearly to the other GPDs. Now, in this graph, you can see a very visual way of showing the effects of each parameter on the GPDs. And in addition, another way of studying this effect is by looking at these so-called envelopes. These envelopes are created by taking one of these parameters and varying them by a factor. In these case, these parameters were varied by the same factor, up to the same factor. And you can see that these curves these graphs are very different. On the left-hand side, this one is very smooth, it's very continuous, uniform, and on the right, you can see it is not and very sporadic. In addition, we can compare our parameterization to other groups. In this case, we are comparing against Aliekin. And you can see this purple curve here is the ratio between our GPD parameterization and Aliekin at the same Q squared of 5 Jev squared. And you can see that our parameterization falls within the expected error for this particular group, especially at low Bjork and X below 0.1. Now, due to the complexity of GBDs, we have started with comparing our leading order terms, but this transitions very nicely into future work, as all work done up to now is done with leading order terms, but there have been studies showing a potential large effect of the next leading order terms. In addition, another logical step would be to take the Fourier transform of the GBDs in order to construct the spatial distribution of partons. This will allow us to eventually visualize the proton in a method analogous to the famous imaging of the black hole. And I would just like to thank Brandon for his help programming and debugging, and Professor Luidi for her vast knowledge on this field. Thank you very much for your attention.